So let me start by telling you what's going on. So we have a quiz today. Then we have exam 2. Next Thursday. And the topics for this second test are going to be everything up through Newton's laws. And remember that everything in this class is cumulative, so you need to go back and be ready for old questions too, okay? So I mentioned this before, but it's probably worth mentioning again. Like, in my opinion, the best way to get ready for this exam and to get ready for all my tests is to go back over the daily assignments, go back to the beginning, look at the first question, and ask yourself, do I know the steps to solve this problem? And if you do, you know you do this, 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 then you probably don't have to spend any more time on that, you know. But eventually, as you go through one by one, all these problems all the way through, you'll get to some where you're sort of hazy on what to do. And then those are the ones you need to spend a little time on, okay? Obviously, this test isn't going to have all of those problems on it, but I basically just do like a random sampling of problem types, you know? So if you're ready for all the problems, then you'll do well on the test, you know? If you're ready for half the problems, then you're rolling the dice, you know what I mean? Anybody have any questions about the exam? Okay. Anybody have any homework questions you want me to go over? All right. So I'm going to start out by talking about Newton's third law. And so, okay, Newton's third law. And I'm first going to tell you, so you've heard a paraphrase of how Newton wrote about this before. It to me is the least useful way that you can think about this, but I just want you to connect to, like, when someone mentions this at a fancy cocktail party, you can be like, oh, Newton's third law, I know that. So this is for, okay, every action has an equal and opposite reaction. Maybe the way language was in England in 1750 or whatever, this made some kind of useful mathematical sense. To us, it doesn't really make any mathematical sense, so I'm going to give you a better way to think about it. But I want to talk about this as the third common misconception in this class, because this is one of the trickiest things, one of the things that's hardest for people to wrap their heads around. So I want to go back through the other common misconceptions. So we've done 2 of them so far. Who remembers what the first one is?
And the one that where if you launch the object, the velocity is 0 on the top, or was it the one?
Both of the 2 we've done so far had videos associated with them. Yeah. Yeah, that's right. So the first one is, so the misconception is that gravity makes heavier things fall faster. What actually is the case is that without air resistance, gravity makes any two objects, let's say gravity makes all objects accelerate down at 9.81 meters per second squared. Okay, so that's the first one. And most people grow up picturing that wrong in their heads. And so you need to kind of go back and violently, actively replace your old thinking with the new thinking, you know? Rip it out of there. Anybody have any questions about that one? Comments? Anyone who doesn't believe this for 1 second? Okay. So that video was doctored, etc. Somebody just left like a whole bunch of pamphlets in the physics mailboxes about, it wasn't about gravity, it was about, although, you know, flat earth people don't believe in gravity. I don't know if you know that. I don't know what they really believe makes things fall down, but they don't, gravity is not it. But these pamphlets were left about the conspiracy of global governments controlling the weather for political gain. And it's given me a lot to think about. What with aerosol seeding and large engine whatnot. I don't know. I'll give you a pamphlet on it. Okay. Common misconception number 2. Who remembers what that one was? This one also had a video that I showed you. Yeah.
An object shot
Yeah.
from a certain height and an object drop from the same
That's right.
and the same weight will hit the ground at the same time.
That's right. And so the way I think of this one is the misconception is that, let's see, objects moving horizontally aren't affected by gravity the same way, let's say. Aren't affected the same way by gravity. Okay. In fact, so actually, no matter what is going on with an object, whether it's sitting on a table or flying through the air or rolling, no matter what's happening, gravity always applies a downward force of the mass times 9.81 meters per second squared. Okay, so the motion doesn't affect anything, and that's why a bullet hits the ground if it's fired in the same amount of time that it does if it's dropped. Gravity's pulling on it just as hard whether it's moving or not. Okay. And now, common misconception number 3, the whole reason I'm talking about these right now. The misconception that people have is that in a collision, there's sort of, I think people sort of think of it as like a winner and a loser. So in a collision, there's a winner and a loser. And the winner applies a bigger force to the loser than vice versa. Okay. What's actually going on in a collision or any time two objects are in contact. So I'm going to say at any instant where two objects are in contact, they apply the same force to each other. Those forces are in opposite directions, so I'll put that in parentheses for now. Okay, so think about how weird this sounds for a second. Like, if you're driving your SUV at 60 miles an hour and you hit a bug, this ridiculous, this guy should be writing pamphlets about this. This is absurd, okay? This is saying that your SUV hits a bug, the SUV applies a force to the bug applies the exact same force to the car. It just doesn't sound possible, okay? But that just is what it is. Let me try to, let's think of a couple of cases where it sounds really crazy, and we'll try to make sense out of it, okay? Okay, so yes, it sounds crazy at first, okay? So like if a truck hits a bug, the bug applies the same force to the truck as the truck does to the bug. Let's make up a force that each of them apply to each other. Okay, so this truck hits a bug with its windshield. Let's say there's 20 newtons of force. Okay, so the bug applies a force of 20 newtons. So let's draw these free body diagrams.
And why are bugs not breaking windshields left and right?
Yeah, right. That's exactly the kind of question that we are going to try to answer, okay? So I don't know what a bug looks like. This is supposed to be a fly. That's a terrible bug.
It's beautiful.
Okay, so there's the bug. So let's say that we have so there's a weight force that's very small because the bug is really light. So I'll call that little mg. And then the main thing we're concerned about here is there's a pushing force on the bug. let's say this is 20 newtons. Okay. And then let's draw the free body diagram of the truck. It's a Chevy Suburban or a school bus. There's a big weight on this, big mass. There's a pushing force from the ground. And then what I'm saying is there's a 20 Newton force that the bug applies to the windshield. Okay? Well, we know that when this happens, the bug accelerates so much so fast that it basically disintegrates, you know? The truck, you hear the noise, but you don't feel any acceleration or anything. But now let's think about the masses of these two things, okay? So the mass of the bug is, what do you think a mass of a bug is? Let's say 1 gram. Lower? Okay, so the mass of the bug is 0.0002 kilograms, okay? A fifth of a gram. And the mass of the truck is, well, what's the mass? 2,000 kilograms? So let's go Newton's second law for these two things. Okay, so first I'll do it for the bug. Okay. Looking at this free body diagram, we have 0, negative mg. I'm not worried about that as a number. Well, we can put numbers on it, I guess. So 0.0002 times 9.81 is negative 0.0020. And then we have the 20 Newton force. That's in the negative x direction. If I'm looking at the free body diagram of the bug. So this is going to be 20, 0. And all this is equal to 0.0002, the mass of the bug, times its acceleration, which is happening in the x direction. And so the y component, well, I guess it's also going to be, it's going to have some acceleration there. That's not the point of this problem, though, so I'm just going to leave that out. What we care about here is the x equation. So it says negative 20 is equal to 0.0002 times a. And so a is negative 100,000 meters per second squared. Okay? So that's the kind of acceleration that makes something disintegrate onto a windshield. Okay? And now let's think about what happens to the truck. The free body diagram says we have a downward force of, so that, 2,000, no, I did, of that, that's the weight. A normal force. And then the horizontal force from the bug. This time it's in the positive x direction, 20 newtons. and this is equal to the mass of the truck times the acceleration. So this time the x component of this equation says 20 is equal to 2,000 a. And so the acceleration of the truck is equal to 0.01 meters per second squared. Okay, so the same force was applied to each one by the other one, but the result of that force is vastly different, and the difference comes from the different masses, usually comes from the different masses. In this case, it does. Okay. So it's the same force, but the effect on the two objects depends on their masses. Okay, so I don't know, maybe thinking of this as a bug might be a stretch, but think about, I don't know, think of what's the biggest bug you can think of, you know, a giant beetle or something. If you imagine a car trying to break the world land speed record, hitting a giant beetle going at 1,000, meters per second or whatever the speed is, that bug is going to disintegrate even more completely, right? But that bug actually starts to have a chance of breaking that windshield because that contact force from the speed is just getting bigger, and eventually, like, that contact force gets big enough that it has a noticeable effect on the winner of the collision too. Okay. Anybody have any questions about that? Want to ask any questions to help clarify this? So, but this is the deal, and we're going to spend some time in lab talking about this too. The bug they apply the same force to each other in opposite directions, but that force of 20 newtons sends this bug into the fifth dimension and has no noticeable effect on the car, Okay, what about another case where this doesn't make a lot of sense at first thought? So let's think about a baseball bat hitting a baseball. Can't fit the guy's whole head in there. Okay, so this guy swings this bat. Hits this ball. I think we can all agree that if you're going to call something a winner and something a loser in this, the player and the bat are the winners, the ball is the loser. You never see a case where the player and the bat go flying and the ball stays there. You know what I mean? So what's going on? Like in this case, this is a pretty short duration. of impact. And this force would be really, really high. So let's say maybe 10,000 newtons is the contact force. But again, now think about the effect that 10,000 newtons of force would have on both of these two participants, okay? The ball has a very small mass, like 0.1 kilograms, okay? So if you apply 10,000 newtons of force to something with a mass of 0.1, you get a gigantic acceleration, and that's what happens with a baseball, okay? Now, what about the bat? The bat has a bigger mass than 0.1 kilograms, but then the bat is also being held by a person who has a mass of, weighs 200 pounds. Has a mass of 100 kilograms. And then that person is also standing on the ground with spiked shoes on, dug into the ground. And obviously, like, the earth has quite a bit of mass, And so the effect is that even though they each apply 10,000 newtons of force to each other, the ball goes flying and the person in the bat are relatively unaffected. Okay? So hopefully just little by little thinking through these examples, you can start to be like, okay, maybe. I still don't totally buy it, but maybe, Like, that's all I want right now. No, I do want you to buy it, but okay, and then one other thing about the baseball example is, so just like if you drive the car fast enough, the bug could potentially break the windshield. Like, if airplanes hit birds, it smashes in the windshield of the plane. It's a total catastrophe, That happens sometimes. So how can we think about the fact that this ball is also applying a big force to the bat? And the harder the person swings the bat, the more force the ball applies to the bat. Well, I think probably any of you who played baseball as kids, you probably used aluminum bats, but back in my day, like half the people on the team used wooden bats. And so sometimes wooden bats break, okay? And like when I was 9 or whatever, 11, playing baseball, I didn't swing very hard. The pitcher didn't throw very hard. And so that contact force wasn't very big, And so if I got a broken bat, here's how it went. Like, I'd swing, and my coach would hear like a funny noise, think something sounded funny. He'd take my bat and tap it on the ground. And if there was like a little rattle, he'd be like, oh, there's a little crack in there somewhere. Okay? Like, it was a very, like, I wouldn't have even known anything was wrong, Have you ever seen like a bat break in a professional baseball game where they throw 100 miles an hour and the people are all on steroids? It doesn't look like that. The coach doesn't come over and check to see if there's a little crack in it. The bat explodes into multiple pieces, some of which go flying towards the stands and the players and stuff, okay? What that is that contact force getting so big that even though the bat is still kind of the winner, the ball destroys the bat, okay? Another example, how about, can I draw this? I haven't tried to draw this before. Do you think I'm going to go drawing all these hexagons on this soccer ball?
Yes.
I think maybe I shouldn't. Okay, so imagine kicking this soccer ball. Okay, so first of all, imagine it being like a gentle kick. Okay, your foot is going to win this competition, right? Again, like the ball is the thing that flies off your foot, not you don't go flying away from the ball. But think of a gentle kick with a bare foot like this on a soccer ball. No problem, right? Like if somebody was standing right there by that chair and I was barefoot, I'd have no problem kicking the ball to them. But now imagine that somebody is 50 yards away from you and you're barefoot and they say, hey, kick our ball back to us, You'd have to like run up and kick it. And if you think about doing that, that it's not going to feel very good, you know? It's going to hurt your foot. The reason it's going to hurt your foot is because when you run up and kick the ball harder, it creates a bigger contact force. You need that bigger contact force to make the ball go farther. But that bigger contact force also is acting on your foot, and that's the pain that you feel. Okay? So, the answer is yes. There might be a winner and a loser, but each one of those two things applies the same force to the other. Always. That's just always the case. Whether it's two things just leaning against each other or whether it's like a rapid collision or anything like that. Okay, so I'm going to give you sort of a mathematical version of Newton's second law. Newton's third law, sorry. So Newton's third law, in a form that makes it easier to use mathematically.
Was Newton actually the person that came up with all these laws?
Newton, Isaac Newton, Sir Isaac Newton. Some people would say the smartest scientist in the history of the world is Einstein. And you could make that argument, but the other half of people would say that it's Isaac Newton. He came up with all of the laws of classical physics that we use that defined physics until Einstein, basically. He invented calculus because there wasn't adequate math for his new laws of physics. So he's like, I better invent some new math so my new laws work. And he then applied all of these laws of physics to to planetary motion to figure out stuff about astronomy. Yeah. Pretty hard to imagine the influence he's had on the world. And I think that was in about the mid 1700s. Okay, so mathematically, the way you want to think about Newton's third law, every action has an equal and opposite reaction thing, is if bodies A and B are in contact, then the force on body A by body B is the opposite of the force on body B by body A. Okay, so those forces have the same magnitude in their opposite directions. That's what that negative means. Okay, so I just want to do one example problem where I show kind of how this works in the type of problems that we've been doing. So let's say, the examples that we've done with multiple bodies, I think have pretty much just been with two bodies. So let's do one with three. And these are all in contact. And let's say this is 5 kilograms. The one in the middle is 8 kilograms. And the one on the right is 2 kilograms. And there's a force applied this way of 20 newtons. And we want to calculate the force vector applied on the 8 kilogram, applied to the 8 kilogram by the 2 kilogram. Okay. So what's the first step in a problem like this?
Free body diagram.
Yep, and what do we want to use as our chosen body? The whole thing, yep. So we're going to choose the whole thing, calculate the acceleration, and then we'll go to an individual body. So free body diagram of the whole thing. So we have a weight force down. The mass of the whole thing is 15 kilograms. So this is 147.15. And then we have a pushing force up from the ground. I'll call that N total. And then we have the force of 20 newtons here. There's no other contact with the boundary. So now we'll go to Newton's second law. And it says 0, negative 147.15 plus 0 N total is equal to, no, not is equal to, one more force, plus negative 20, 0 is equal to the mass of 15 times, okay, I didn't write this here, but is this moving free to move along the X or Y axis? X, so I'll write this as A0. And then the X equation says negative 20 is equal to 15A. So A is equal to 4/3, so 1.3 repeating meters per second squared, negative. Yes?
Can 20 be positive as well?
Can 20 be positive? I mean, if I had put the force on the other side and drawn it in the other direction, it could be positive. But you have to deal with the direction that it's in. You know, we're using a coordinate system like this. So that force is in the negative X direction.
Oh.
Okay, and so from this, plug this into the acceleration vector, and you get that the acceleration vector is negative 1.30. Okay? Everyone good with the calculation of the acceleration? Okay, now we're going to choose a body to isolate in order to calculate that contact force. But I'm not gonna do this, but I'm just gonna sort of explain. Maybe you can sort of picture what's happening. We're trying to calculate a force on the 8 kilogram body, right? So what we'd like to do is isolate the 8 kilogram cart, but that has two unknown horizontal forces acting on it. One that we're trying to calculate from the 2, but then another one that we don't care about from the 5. And the fact that we have those two horizontal forces would mean that when we came up with our horizontal equation, we couldn't solve for it. Okay? We have one equation and two variables. So what can we do instead? Instead, I'm going to isolate the 2 kilogram cart, okay? Calculate the force on the 2 by the 8, and then use Newton's third law to figure out what the force on the 8 by the 2 is. Yes?
Wait, why wouldn't it?
Okay, let me, okay, so if I draw a free body diagram of the 8, I guess I'll draw this and just not go through the calculations. We have a downward force of 78.48, an upward force of N8, and then horizontally, we have a pushing force here from the, I'll call this R right, and over here we have a pushing force, I'll call this R left. Okay. And the problem is when we go to Newton's second law, we can only have one variable in each equation, and this has two variables. We don't know either one of these, okay? So we wouldn't be able to calculate either one from this free body diagram. Okay, so that's the problem. So the problem is there's two horizontal variables and only one horizontal equation. So instead, I'm going to draw a free body diagram of the two. There's a weight force down of 19.62. There's a pushing force up of N2. There's a 20 Newton force here. And then over here, there's a pushing force, I'll just call it R. And that's a pushing force. This is the force on the 2 by the 8. Okay, and we're going to calculate that. So Newton's second law says R0 plus 0, negative 19.62 plus 0 N2 plus negative 20, 0 is equal to the mass 2 times the acceleration we calculated, 1.3 repeating 0. Any questions about Newton's second law there? And now the x equation says R minus 20 is equal to negative 2.6 repeating. And so R is equal to positive 17.3 repeating newtons. This vector is the force on the 2 by the 8. Okay, so if I plug this in here, I get that the force on the 2 by the 8 is equal to 17.3 repeating 0. Or in other words, that's a force going this way with a magnitude of 17.3 repeating. But that's not quite what we're asked for. We're asked for the force on the 8 by the 2. So now you can use Newton's third law. And it says the force on the 8 by the 2 is negative 1 times what we just got. Which is negative 17.3 repeating 0 newtons, or going in the negative x direction with a magnitude of 17.3 repeating. Okay, so anytime you calculate the force on one thing, like say a body A by a body B, you also know the force on body B by body A. Okay, you just have to switch the direction. Okay, so say you're given that the force on a whale by a diver, we have no idea what's going on. This sounds terrible. But the force on the whale by a diver is negative 86.4, positive 190.6 newtons. Okay, that's all we know. And we want to know what's the force on the diver by the whale. Because we're human-centric. That's what we care about. Okay? The answer is, the force on the diver by the whale is -1 times the force on the whale by the diver, which is positive 86.4, negative 190.6. And you didn't have to know anything about how this horrible event came to be or anything, You just know that if you're just switching which is acting on which, if that's all you're doing, then you're just taking the opposite of that. Okay? Any questions about that? And actually, this is the reason that, so I gave it to you just sort of as a rule to follow before, that when you're dealing with pushing forces, if you have two bodies pushing on each other, they should have the same variable name. Newton's third law is the reason for that. Okay, so because what you're doing is just changing which body is being acted on and which body is acting. And so all you do is change the direction of it, switch the direction of it. Okay. So the next topic is circular motion. And almost everything you need to know about this is stuff that we've done in labs so far. So most of understanding circular motion is like labs we've done. Okay, so here's what I mean. So imagine an object's moving around a circular path like this. I guess I'll call that circular. Let's say that it's going this way and slowing down. Okay. Well, there's a lot of things that we already know how to say about the velocity direction, the accelerations of the parts of acceleration. The velocity is going to be tangent to this path in the direction of motion. So there's the velocity direction. It's slowing down, so the parallel part of the acceleration is opposite the velocity. I always say you can find the direction of the perpendicular part of the acceleration by fitting a circle to the curve. Well, this is already a circle, so the perpendicular acceleration just goes toward the center of this circle. So that's a perpendicular. In labs, we just say, okay, from this, we can come up with a range of possible acceleration directions in between those two. But remember that where that comes from is that the total acceleration is just equal to the sum of these two parts. So in class, instead of coming up with a range of directions, we're going to actually be able to calculate these and just add them together to get the total acceleration. Bless you. Okay. So that stuff should all look familiar. There are only 3 new things that you need to know for circular motion. So only 3 new things you need for circular motion. And 2 of those are just new names. We could keep the old names, but people have already named this stuff, so just to communicate with people, we have to sort of go along with the way people do things. Okay, so the first one of these is for circular motion. A parallel has its own name only for circular motion, and it's called the tangential acceleration. And that's a pretty good descriptive name of this, because that A parallel is tangent to the path of the motion. Okay. So that's something you have to remember, but it's just calling something a new name. It doesn't change the meaning at all. The second one is also just naming. So for circular motion, a perpendicular is called the centripetal acceleration. Okay. This one the meaning isn't quite as obvious because that looks like a made-up word, but centripetal really just means toward the center. And so then it makes perfect sense too. This is just the part of the acceleration toward the center of the circle. Okay. And then the last one, the only one that really that's really new information, is that the magnitude of the centripetal acceleration is always the speed squared divided by the radius of the circle. So v is the speed of the object and r is the radius of the circular path. Okay. So in order for something to turn, there needs to be a perpendicular acceleration, right? Well, if it's going to be going exactly in a circle, that's a very specific amount of turning that it has to do, okay? And it turns out that that specific amount of turning requires an acceleration that's equal to the speed squared divided by the radius, okay? So that's the only new mathematical thing we have. And other than that, I think all of this will look pretty familiar, okay? I want to say one more thing before we do the quiz. Why do we care about circular motion? Do you think we're going to do circular motion and then we're going to do octagon motion and then triangle motion and all, like what's special about the shape of a circle? The answer is really that when rigid bodies move, bodies that don't really stretch or deform too much, every point on that rigid body is moving in a circular path. Okay, so like if so say I keep my arm straight and like swing it around like this, holding like a glow stick or something, and it's dark, you'd see a circular path. So there's a connection between circular motion and the motion of rigid bodies. And rigid bodies are this really important thing that come up in a lot of, especially engineering calculations, but lots of physics calculations. And so that's why we're doing circular motion, and we're not going to do squares and octagons and whatever. Okay, so I will get into, we'll get into doing calculations for circular motion next time. Anybody have any questions about what I brought up so far? All right, let's do the quiz.